Good evening, ladies and gentlemen. I'm glad to see all you here. And I was actually surprised that so many participants have the interest to this topic, but it's another evidence that this theme is very important and the topic is pretty hot for nowadays. Today, I'm going to talk about the new material for semiconductor industry and what challenges we have in the sustainability in for sustainable production. My talk, I will briefly describe in an introduction why the sustainability is important, who we are and what we are doing here at EZM ASSID, and also describe very briefly the Bosch process. Why do we need the Bosch process? What we can achieve using this method. And after that, we come to the TSV cleaning. And finally, we will review the results that we could achieve. Before we start, so in our days, sustainability becomes a challenge for microelectronic production. All we get the pressure. We have a pressure from the society, we have a pressure from the politics, and we have also responsibility to make our microelectronic production more, and not only reliable, but it also needs to be sustainable. The biggest company, high-tech company, they also checking their supply chains and they asking what kind of materials do they use for production of the chips and dies, what kind of liquid do they use, how do they treat them, how they weight them, and not all chemicals are really very friendly to the environment, and that's why it's we have to find some solutions that to substitute the dangerous hazardous components. At the same time, this new substitution have to perform also very good as today's material, but also important is the price, how much we have to pay for the new chemicals. So this is a task we have to, and we need to find a solution. At Fraunhofer by itself, we have one public project called Green ICT, and within this project, we have a possibility to test something new. In this case, I mean, we can test the new chemicals. We can find a way how to save the energy or to reduce the cost for energy consumption. And this is very good because for a big plant, it's a problem because they cannot test very easily. We are completely equipped as the same way as a production big plants. We have a fully automated lines for 200, 300 millimeters wafer processing. And at the same time, we can change the materials without big problems, without big issues. And in this project, we started to look what kind of material we can substitute, what actually what actually mean for us a hazardous material. And we reviewed all our processes. I have to mention that I belong to the back-end of line metallization group. So here we have the plating tools, we have a CMP, we have the tool for wet etch, strip processes, and one of the process is a cleaning. So cleaning of 200, 300 millimeters wafer. And after this critical look into our processes, we have found that one material actually looks very good, but it's not really fulfilling the HSE requirements. And we started to analyze it, and the material that we are using for TSV fluorpolymer removal is called EKC 265 from Dupont. And why this material is not good enough? Actually, it performs very good. So it's do what it's supposed to do. but it's the component or the additives that used for this material are pretty hazardous and also classified as cancerogenic under REACH. It's not really fulfill the sustainability requirements at all. So we have decided to find a substitution in this particular case. And we, after some research we have done, we have connection to different chemical suppliers, vendors. We found a material called D-BOS from Technic France, D-BOS 390. And they also published some results. But the results they published was done on the bond level. And we wanted to prove if this material also will perform so good on the wafer level. But by the way, they have claimed that material has a dual function, could remove this positive photoresist, could also remove the fluorpolymers, and it's also confirmed from the safety point of view. And about the stability, they say about 8 hours, but let's check it. And what is also very important, that material could be, the wafer processed using this material could be directly rinsed by water. And that was a strong argument for us to test it. So, okay, so far so good. Let's see how the SDA's data sheet looks like. And we have internally reviewed the technical data sheet, and we do not see here any hazardous in comparison to EKC materials or components. But how does this chemistry perform on the wafer level? Does it could really remove all the fluorpolymers? It was still open questions. And before we start to go to the TSVs, let me describe why actually who we are and why do we need the TSVs. ASSID, it's an all silicon system integration Dresden Institute. Our core competence is in the packaging. So we are producing the interposer 2.5D or 3D integration, heterogeneous integration. So we integrate a passive active device on the interposer. We can work with a wafer, we can work also using the polyamides. But to create an interposer, there is something important is needed. And this important is the interconnections for heterogeneous integrations. And this interconnects, you can see there, these pillars. This is vias or the TSVs etched in the silicon in the silicon wafer. But to get them, the way is pretty complicated. To receive them, we need to apply the special approach and so-called plasma etch, and the most or very widely it's called Bosch process. And I will very briefly describe you what the Bosch process is. For a Bosch process, probably all the participants know much better than me, but by the way, in the Bosch process, we have the cycle of 3 very important steps. One step is the fluorpolymer will be deposited on the walls. After that, the fluorpolymer will be anisotropic etched from the top. And the next or the third step, it's an isotropical etching of silicium using the SF6 plasma gas. And this process or these cycles repeat all the time. And using this process, it's possible to etch different dimensions or geometries of TSVs. But after etching of TSVs, the walls of TSVs are covered by this fluorpolymer passivation layer. It was covering from the top to the bottom. And this layer is there to protect from isotropical etch the walls to get this nice etched vias. But after etching, the polymers needs to be removed. And why they needs to be removed? First of all, the fluorpolymers, they have a bad adhesion to the silicon surface, and they can peel off anytime. Additionally, when the further steps happen, like a silicon dioxide in CFOD or metal sputter process taking place, the whole system can fall down, so it can delaminate. It could lead to higher thermal stress. It could lead to the electrical malfunctioning, failure. So the clear answer is it needs to be completely washed away. And the picture of not cleaned TSV, it's very easy to identify. We do not see on the bottom any clear scallops caused by Bosch process. And everything is covered by fluorpolymer layer. And how this layer needs to be removed, I will explain in a few minutes. And this is another example how the fluorpolymer layer is peeling off from the TSV walls. And on the bottom, there is also a lot of residuals. And for example, if everything is covered by the metal, it could simply just delaminate. For cleaning of TSVs, we are using our existing tool because the challenge is to find something new, but this something new have to fulfill the requirements. First, we don't want to change anything in the equipment. So we're going to use the same equipment, but we want to change chemistry. So here we have in-house existing SSCC cleaning tool, and basically the cleaning step consists from the immersion into the soak station. After it takes some time, let's say 35, 36 minutes, and the wafer after that will be rinsed by chemicals again and rinsed by isopropanol, because the water cannot contact directly to EKC in this particular case. And the third chamber, in the third chamber, it's happened following that we will finally rinse by water and use megasonic power energy to remove all the particles, and the wafer will be dried by nitrogen. This is the first method we're going to use in our testing. Another technology approach, it's so-called MACPI. And for MACPI, we have contacted the external company. This process is patented by the process. And very briefly, I will describe this. The idea is completely different in comparison to SSCC. We will apply, using this triangle, the megasonic energy into the wafer surface, and megasonic energy is much higher in comparison to SSCC. But the energy will be transferred through the fluid layer into the wafer surface. And in both cases, SSCC, our existing tool, or MACPI technology, we will use the same chemistry from Technic France D-BOS 390. The idea of MACPI was realized by, again, external company called They have built the tools for handling of 200 and 300 millimeters wafer, and all the demos was done by them. They also claim that using this technology, it's possible to reduce the process time and also use the lower temperatures. And so far, so good, but let me go to the most interesting part, how it actually performs. Does this chemistry works or not? In here in-house, we have a different design of TSVs, but one of the very important design is a 260 micrometers deep TSVs and 80 microns CDs opening. It's pretty large TSV, and first results I'm showing here. This is our reference sample. So the wafer was cleaned using ASSID, using our POR method, and this is the example how the clean TSV needs to look like. So on the left, we can see actually not much, but the structure of the walls looks pretty clear. But under the another magnification from the middle, we very good can see the scallops created by the Bosch process. So all the fluorpolymer was completely removed in this case. And after we have checked the bottom of TSV and the same picture, the bottom looks absolutely clean and very nice etched silicon is to see. So after that, we have started to evaluate the D-BOS chemistry. We have filled it in our SSEC tool, and the first results, was the first test we run, and to be on the safe side, we just doubled the process time because we wasn't sure if the POR will work, and we doubled the process soaking process time. And what we see, the TSV actually looks very good. In the middle of TSVs, there is no visual residuals. The shape of the etched silicon looks good, and on the bottom, no particles, no residuals, absolutely everything was completely washed out. So after this successful results, we started to optimize the process and to see what's happened actually if we reduce the process time or soak time. We have reduced the soak time to the same time as in case of ASSID, and the results looks also very promising. We visually do not see any residuals on the middle of TSV and on the bottom. I'm showing at the moment only 3 pictures, but it was done a lot of cross-section picture at different places, and then centrum, half radius, edge. We have analyzed it completely from the top to the bottom. But to be definitely sure that the material performs as it needs to perform, we did the EDX analysis on the middle of TSVs and on the bottom. And what we see, there is no carbon fluor bonds, reflex, or signals was found in this particular case. And the spectrum we see here, the experiment was performed after 36 minutes of process soaking time. So actually, I was surprised that the chemistry looks pretty good. It was a first try on our existing tool, but the next try that we used another approach, completely new for us approach and technology, MACPI. I'm showing you on the left side the best result I could achieve for this moment, but the way wasn't very easy. First of all, because MACPI running at lower temperature as we run here on our SSEC tool. The second, the process time was also reduced or shorter. But by the way, we could, let me say, almost receive, but it's not clean, their TSVs. So there is some melted or swollen residuals are still visible. So we have found a spot exactly on the middle of TSV, and you can see it on the right side. And on the left side, there is some small residuals on the top of TSVs. Bottom and the rest of the TSV was absolutely cleaned. We have inspected at least at 3 places each wafer, and we couldn't find any other residuals. So 20 minutes at 55 degrees C using the MACPI technology works. It could clean the TSV, but not for 100%. It's a further optimization. It needs to, is required. We also did the EDX analysis of TSV cleaning by MACPI technology. What do we see here? On the places where no residual visible, there is no fluor signals at all. So this means that the walls and the bottom of TSV are really clean. So it was the first try with this chemistry, and with the TSV 260 to 80 micrometers. But in-house, we still have another dimension of TSV. And one of the dimensions that we very widely used is a 10:1 dimension, critical aspect ratio. And the dimensions of the TSV is a 10:1. So the 10 micron opening and 100 microns deep etch. So here in this case, we have also performed the cleaning using the EKC chemistry. And after that, we will compare the results to D-BOS. So what do we see here on the left side? The left side shows us that the middle of TSV looks pretty clean. Of course, the surface looks different in comparison to the big TSV that I showed before, but it's a slightly different process, and it's completely different dimensions. It could not be directly compared. And bottom of TSV looks also absolutely clean, and no residual is visible. Then we have changed that chemistry and run another test. And what do we see here? And this test we ran for 36-minute soaking time. So actually the time wasn't doubled. And the results was really good. So in the middle of TSV, no residuals was found. The bottom of TSV is absolutely clean. But to double check it, we have performed the EDX analysis. And EDX analysis just confirmed our suggestion that the TSV was completely removed. The fluorpolymer was completely removed from the TSVs, and no residuals was found in this particular case. If to summarize the results, I was actually very surprised to see good results. And the MACPI process still need the optimization, but it's also offer another positive points like lower temperature and shorter process time. Very important, really very important point that the chemistry could be, the wafer processed using the D-BOS could be rinsed by water. And it also can influence on the costs, but the further evaluation is still ongoing, and we need to test we need to repeat the results on the same structure. We need to repeat the results on a different structure and to see how does it behave. And actually, this is not a finish. This is just the beginning of our way. But I'm really happy that I could do it in with the external two companies like Amcos and Process. I was really happy that I got a support from my team, or not my team, the team that I allowed to work. And actually, because of the green ICT, they gave us a light push to find a solution, and we will keep working in this direction. All the results that we will achieve in green ICT project will be published later, and the industry company will receive the offer what kind of substitutions they can use for their processes, and we of course will give it evidence if it works or not. So now I'm open for your question if you have any.